our first sort of speaker, not sort of speaker, you are a speaker, following that, sort of giving us the deep background into what we're going to be talking about topic-wise, and that is Thomas Wong. He's an associate professor of physics at Creighton and a researcher in quantum computing algorithms, former high school teacher, and author of an introductory quantum computing textbook, and creator of Qubit Touchdown, which is, there's several on the tables and spread out that I think we're going to use a bit. He spent 3 years at the National Quantum Coordination Office that Jake mentioned at the White House, and 2 years concurrently at the Department of Energy as a program manager in QIST. And to add to that, his textbook is open source, free online. You can print it. You're probably going to talk about this, but I have to kind of pump your tires because I use it a lot. It's one of I love it as a resource. It's great for any students who come to me and I don't have the bandwidth to talk to them all. I'm like, oh, just read this. It's better than what I'll do in that. So freely available, awesome resource, and we're going to hear more about it. So question?
I'm going to use that textbook.
Yeah.
I picked it because it's free and because it has exercises, but I was dreading, are there solutions to those exercises? But there are. There's a textbook with exercise and solutions.
Checks all my boxes. So anyway, with that, we're around for Thomas Wong, who's going to keep us going.
Thank you, Justin. Yeah, so my name is Tom. You guys will have 4 hours with me, so I guess I can share a little bit about me and my institution so you understand kind of how this course is based on my students and how you might adapt that for yours. So as Justin mentioned, I work in quantum algorithms. That was my PhD thesis, and I've been working on it ever since. I also was a former high school math teacher. What else? I've been married for almost 10 years now. We've got 3 kids, ages 4, 3, and 4 months. So besides quantum, my other interest is work-life balance and parenting in having both parents that are working full-time. So happy to talk about that as well. Creighton University is a Catholic Jesuit liberal arts college in Omaha, Nebraska. So the California equivalent would be Santa Clara University in the Bay Area, the University of San Francisco in the Bay Area, and Loyola Marymount in LA. And so there are similar institutions, but with different strengths. For example, Santa Clara University being in Silicon Valley, they have a strong engineering focus. We don't have any engineering at all. We have a 3-2 program where you can do 3 years at Creighton and then 2 years at an engineering school, but there's no engineering at Creighton, for example. Most students go to Creighton because they're interested in the health sciences. So we have a med school, a dental school, a pharmacy school, nursing school, physical therapy, occupational therapy. You name something health sciences related, we have that. And so because of that, we're not technically classified as a primarily undergraduate institution, but functionally, day to day, we're like a primary undergraduate institution. So we have 4,000 undergrads and another 4,000 graduate students, but in these medical fields or MBA, things like that. But we don't have a PhD program in physics or anything. And so with that in mind, we get a lot of students in the physics department because they started off pre-med and realized freshman year that they hate biology and or chemistry, but they're interested in science and they make their ways to physics. And so that affects things. So for example, my Introduction to Quantum course that I teach, linear algebra is not a prerequisite. Even though all of our students will eventually take linear algebra, they may not take it until later because they switch from pre-med to physics. And so we end up learning some linear algebra as we go. So you can think of it as an intro quantum computing class for STEM majors who are interested in learning the math and will eventually learn the math, but haven't yet. And so that's kind of how this intro is going to go as well. So thinking about your students, you can think, oh, if your students already know linear algebra, you can jump in much more quickly and deeply, whereas my intro is going to be slower. All right, so we're going to start off by talking about Qubit Touchdown, which you guys can see on all of your tables there. So this is a game that I created actually for my class in 2019. It's because I first taught my class in 2018. I used IBM's quantum computing board game, which I still use. But their game begins with 2 quantum bits, and I wanted a game that started with 1 quantum bit. And so I made one. And being in the Midwest, football is kind of the thing. And so qubit touchdown makes a lot of sense. So this is a football-themed quantum computing board game. You can actually make your own copy. So if you go to my website, thomaswong.net, you can see printables for the board. For the cards, you can print them on cardstock and cut them out, or you can just like write the cards on index cards. Instead of this binary die that has 0 and 1, there's all sorts of ideas of just using a coin and flipping it heads and tails, things like that. So you don't have to complicate it and have a fancy-looking set like that. You can just DIY it. If you want a fancy set, you can buy them print on demand from the Game Crafter. They're an indie board game manufacturer in Madison, Wisconsin, where anyone can upload the artwork to get their own board game created. So if you have an idea for a board game, you can actually get it printed professionally through this service. So that's where these are from. That's why they look so nice. Some new stuff compared to last year is we actually did a study recently on qubit touchdown to see how effective it is with high school students. And so we played this game with 107 public high school students in the Omaha, Nebraska metro. And these students are all either in pre-calc or AP Stats or AP Physics 1. So that's the trig-based physics. And so we're going to go through this study. So I conducted this with them. Oh, not December. It would have been. Sorry, it would have been May 2024. And then we wrote up a paper and submitted it this past January. It's on the archive. So this is a screenshot of the archive paper. And so we're going to use this to kind of see how we introduce qubit touchdown to high schoolers and how you might want to use it in your class as well. So the first thing we did after like the paperwork I had to do being like, do you consent to be part of the study and all this stuff, was I gave them this statement of what a quantum computer is. So I said a quantum computer is a new kind of computer that's based on the laws of quantum physics. It can do certain things faster than normal computers because it follows a different set of rules. And so this is their only knowledge of quantum computing, these 2 sentences. And then they filled out a survey with 2 questions. So I asked them, so they answered on a Likert scale from strongly disagree to strongly agree of I am interested in exploring quantum computing. So just from those 2 sentences. And then I'm confident in my ability to learn quantum computing. So just from the little bit they know, can we gauge their interest and their confidence. After that, I taught them how to play the game, and then they played it. So it's a 2-player game. So we have Taylor Swift versus Ryan Reynolds, right? So I actually Googled, like, who are the most popular celebrities among high schoolers, and they came up. And you can see the game board there. So the football can be in one of 6 positions indicated by those yellow circles. The football can be at 0 or 1 or plus or minus or I or minus I. And Ryan is trying to get the football to Taylor's end zone to score, and Taylor's trying to get the football to Ryan's end zone to score touchdowns. And so they're going to take turns moving the football, trying to get the football to the respective end zones to score touchdowns. And whoever scores the most touchdowns by the time all 52 cards are played wins. So that's it. Let me dive a little bit deeper by giving you a concrete example. So there's 52 cards. You shuffle them, and then you hand out 4 cards to each player. So here's Taylor's cards, and here's Ryan's cards. And you put the remaining 44 cards as a draw pile somewhere in the middle. OK, so in football, you start off by kicking off. So someone's going to kick off. Let's say Taylor kicks off. She does that by rolling the binary die, which is either 0 or 1. And the outcome is a 1. So she kicks the ball, and it lands at 1. And then after you kick off, the other team returns the ball. So now it's Ryan's turn. So Ryan needs to play one of his cards. And what these cards do is indicated by these lines or arrows. So for example, this square root of x, this will move the football along this arrow from 1 to I. If he had an h, it would go to minus and he'd score a touchdown. Unfortunately, he doesn't have an h. If you played x or y, it'd move to 0. And if you play something else that's not labeled here, like you see I doesn't have a line here, Z also doesn't have a line here. So what happens is that if you place those, the ball stays put. And then this thing is a measurement card. It actually says on it what to do. It says that if the ball is at 0 or 1, you do nothing. If it's at I or minus I, then you kick off. So it's like punting the ball. All right, so Ryan can't score a touchdown. He doesn't have an h. So let's say he plays a square root of x and he moves it over to the side. So he'll play that, move the ball, and he'll draw another card so that he has 4 cards again. So you should always have 4 cards until the end when you just play whatever you have remaining. Okay, so Ryan played a card. Now it's Taylor's turn. So Taylor wants to move the ball generally to the right. And so looking at her cards, an X would move it diagonally to -I. A Y would do nothing at this point. S would go backwards, so she would score a touchdown for Ryan, so she definitely doesn't want to do that. And she has an H that would also move it diagonally across. So let's say she plays X. So she'll discard that, move the ball, and then she'll draw another card. Now it's Ryan's turn. So let's say Ryan, again, now Ryan wants to move the ball generally to the left. And so which of his cards will do that? Well, Z will do that. So if he plays a Z, he'll move over there, he'll draw a card. Now it's Taylor's turn. What should Taylor play? What would be the best move for her? Square root of X. So she's trying to move the ball, I guess, or H. Square root of X or H. She's trying to move the ball that way, right? You notice to score, you either need an H or an S. So maybe she wants to save the H for an opportunity to score. So she'll play square root of X, draw another card. Ryan's turn. Okay. Does Ryan want to play an H? No, that's the worst thing he can do because he's scoring for Taylor. Playing an S does what here? Playing an I here does measurement card. Does nothing if it's at 0 or 1. If it's somewhere else, then you punt. So it also does nothing. So it looks like Ryan's best move is to do nothing. Yeah. So let's say he plays an I card to do nothing. Draws another card. Now it's Taylor's turn. What is she going to do? Play an H and score that touchdown. Okay, so now it's 1-0. She draws another card, and she just scored a touchdown, so she's going to kick off. So she kicks off by rolling the die. In this case, it's 0. And then Ryan will then return the ball, and they'll keep on playing until all of the cards are used up. And so at this point, I gave the students an opportunity to play. For the sake of time, maybe we'll save the 10, 15 minutes that it would take to play. And these games, I think, will be here all week, so you guys can play during breaks and so forth. So after they played the game, I then surveyed them again. And so there's a few more questions now. But the first 2 questions are the same, which is, how interested are you in quantum computing? How confident are you in your ability to learn quantum computing? Did you like the game? Was it easy to learn? Okay. After that, I explained how the game that they just played is actually following the rules of quantum computing. And so if you look at the back at every one of the playing cards, you can actually open the boxes if you want to look at the cards. I'll give you 30 seconds if you want to open those boxes. So you can see there's a game board, there's a binary die, there's a little football token that you can move around, and then there's the playing cards. There's also an instructional card and a card explaining the physics that I'll be talking about. But if you look at the back of all of the cards that you play, it looks like this, like a football field. And what's drawn on every card is this sphere that's called a block sphere. And so you can see that it's plotted such that the x-axis is out of the card, the y-axis is to the right, and the z-axis is up. All right, so for a normal computer bit, it can only be in 0 or 1. And if you look at this, you can see 0 and 1 are labeled as the North Pole and the South Pole. So for a normal computer bit, it can only be at the North Pole or the South Pole. But a quantum bit or a qubit can actually be anywhere on this sphere. So it could be at either of the poles, or it could be in the northern hemisphere or southern hemisphere, or on the equator. And this game, instead of using all infinite possibilities, it just uses 6 of the possibilities that are labeled here. So we have 0 and 1 on the z and minus z axis. We have plus and minus on the x-axis, positive and negative. And we have I and minus I on the y-axis, positive and negative. And so when you're moving the football around between those 6 positions on the board, you're actually moving the qubit between these 6 different states. Okay, the way that you do that is by playing quantum gates. So those are the cards that you were playing. So here's one of them, an X gate. And if you look at it, it actually says what this does. It rotates about the x-axis by 180 degrees. So if you have a qubit at 0, and it rotates around the x-axis, so the x-axis is coming out of the card, So it's going to rotate around like that to get, and it's going to end up at the southern hemisphere. So it goes from 0 to 1, and then from 1 it would go back to 0 if you played it again. Similarly, if you're at I and you play an X, you'll rotate 180 degrees to minus I, and if you played it again, you'd go from minus I back to I. And if you're at plus or minus, actually nothing would happen, because if you rotate around the x-axis, you stay put. And so that corresponds to these moves on the game board. So you see how 0 and 1, x will move you between those two. And then I and minus I, x will also move you between those two. And all of the cards have an explanation of what they do. So the square root of x is the square root of that. It rotates by 90 degrees instead of 180. And so if you're at 0, you rotate by 90 degrees, you'll go to minus I, and then you'll rotate to 1, and then I, and then back to 0. And so that's why on the game board, the square root of x has a directional arrow. So you go from 0 to minus I to 1 to I back to 0. So one of the things I was very insistent on when I designed this was that it had to be accurate. Because you know if something is wrong, you know the students are going to remember that, and then it's going to be bad. So this is all accurate to this. And so all of the cards just are different rotations around different axes. Excuse me. So another thing is that even though a qubit can be anywhere on the sphere, you have to ultimately measure and get a result out, which is a 0 or a 1. And so when you measure it, you only get 0 or 1 with some probability. And so if you look at plus, minus, I, and minus I, those are all on the equator. So they're, in some sense, halfway between the North Pole and the South Pole. And so if you were to measure a qubit in one of these states, you should get either the North Pole or the South Pole with probability half-half. And so that corresponds to the die when you kick off. So it's a binary die. You'll notice that it's a 50-50 chance because all of these states are on the equator. And so yeah, so when you play that die or when you kick off, that corresponds to a quantum measurement. So you're getting 0 or 1. All right, so after that explanation, I then surveyed the students again. So there's more questions. The first two are the same questions, which is basically after all that, are you interested in quantum computing? How confident are you in your ability to learn quantum computing? Did playing the game make it easier to learn quantum computing? Were the concepts more familiar because you had already seen them in the game? Did it make learning quantum computing less intimidating? And was it a better learning experience than just learning it without the game? And I think there's one more, which is just would you recommend Qubit Touchdown as a tool for learning quantum computing? And so here are the survey results. So we have all 13 questions, and the percentage of students that responded strongly disagree, disagree, neutral, agree, and strongly agree. It's a lot, so I'm going to kind of focus on some different parts. The first thing are these that I just boxed in red. So these are the questions that are about whether or not students like the game and thought it was easy to learn and would recommend it. And you can see here that students generally like the game. So that's good. But we don't want them to just do something that they like. We want them to learn something or improve their interest or confidence. So these three questions in green, those are all about their interests. So before playing the game, having only heard those 2 sentences about quantum computing, after playing the game in question 3, and then after my explanation in question 7. We're going to analyze this a little bit more on the next slide. And similarly, the remaining questions, the second question in each set, those are about students' confidence in learning quantum computing at those different stages. So let's unpack that, the green one and the blue one about interest and confidence in the next slide. So what we're looking at here is the number of students that responded favorably, meaning they agreed or strongly agreed, and how that shifted going from question 1 to question 3, so after playing the game, and then question 3 to question 7 after my explanation, and then overall going from beginning to the end. And so you can see that from playing the game, students' interest in quantum computing went up by 10.3%. And after I explained it, it actually didn't improve any more beyond that. And so just playing the game, they're like, okay, that increased it, and that was it. In terms of ability, the students' confidence in their ability to learn quantum computing, after playing the game, that rose by 11.3%. And then after I explained the connections to the physics, it rose by an additional 21.5% to end up at a 32.8% increase. Yeah.
So how many students did you survey?
107. Yeah. Yeah.
Was it a voluntary survey? Like, were they forced to do this?
I let students know that the survey was optional. What was it? Teachers brought their entire classes to the library to do this. So I did this over multiple periods. So they had to go and participate as part of the class. But in terms of filling out the survey, I let them know that that was optional, which of course it has to be when you conduct a study. I think everyone chose to do it though. Yeah. I'd give them like the form that outlines their rights and everything and go over it. Yeah. Yeah.
No, we're asking questions. I did not want to interrupt.
Sure.
Before, but I'm going to have a lot of questions for you because of that situation. So if you go back to the block sphere.
Yeah.
So I was here for the workshop last
Yeah.
year.
This one.
And I was late, so I came around this time and missed the rules of the game. And
Yeah.
they didn't give us to play the game, and I didn't. I still thought it was useful to learn like which axis, which gate like rotates around.
Yeah.
But I missed some.
So like
parts.
these.
Yeah, and I still don't know them by heart. But I remember you were the first person out of all the presenters in all the workshops who explained how the block sphere is labeled.
Mm-hmm.
Right, and I think that will help everyone, right? So by convention, the z-axis is the equator, and 0 is up and 1 is down, and then the y is the imaginary axis, right? And then the plus is coming out of the page.
Yeah.
You explained that, and so that's helpful because if you don't know that, then none of this makes sense. But now I have a question because I obviously have to explain this to my students, right? So later on in the book, you finally mention all the points are on the surface of the sphere, right? So that's important to mention.
For
They're
pure
not
states, but we
inside.
don't get into other states in my book. Yeah.
So there might be inside, but we don't talk.
Yeah, we don't talk about that.
Very important to say they're all on the
Yeah.
outside.
I think in the last chapter, it talks about further reading.
Yes.
It includes like actually there's more than what we talked about,
but
right?
So I think we should in the beginning say, okay,
Yeah.
and then there's a place in your book where you say it is not an Earth spinning around, but I think it's a typo. You want to actually say this is an Earth, right? It's a globe. It's a 3D.
Well, it is a sphere, but it's not like a physical object like the Earth is spinning and and then orbiting the sun, right?
But block sphere,
Yeah.
when I first heard of it, it sounded like block.
Yeah.
And I didn't realize it was named after a physicist with that name, right? So
Yeah.
it's also important to say this is somebody's name and not
Yeah.
like
Block
cube
sphere.
that somehow looks like a sphere,
Mhm.
right? And then also I'm not clear on how I'm sorry, I'm losing the question now. I know it was the most important one. So on the block sphere, right? This is a 3D sphere, but the qubit is multi-dimensional. So is this just that in this reality we can only draw 3D?
No, you can always map the state of a qubit to 3 parameters, which would then correspond to a point in 3D space. So,
But in general, like yes, in all the
if you have multiple
parameters of
qubits, yes, it's more
3D,
complicated. But if
right?
you just have a single
yes.
qubit by
yes.
itself, then you can draw it as a a point on the
3D.
block sphere.
And that's okay. That's fair
Yeah.
to say. Even though cube is multidimensional, we're plotting it on a 3D sphere, and that's fair.
Yeah, I think there's a question or comment maybe about that.
Thank you.
Yeah. Oh, yeah, question, sure.
How many of the 107 had enough complex variables to make the connection between the roots and having the argument?
I'm gonna guess very few. Yeah. I mean, I think the way that they accepted it was, they would read this.
It's a fantastic game.
Yeah.
by the way.
Thank you.
Because when you play, it's gonna.
Yeah. I mean, so you saw their backgrounds, right? They were either in a pre-calculus class or AP Stats or AP Physics 1. So, yeah.
This was like 40 minutes with the impact at the front end, or just survey, game, survey, explanation, survey?
Sorry, what was the beginning of
What
the
was
question?
the time, and was there what else was included besides the
everything I showed you was what we did. So it's literally that 2-sentence explanation of quantum computing survey. Here's how you play the game, play it, survey. Here's the physics of it, survey. Yeah.
So maybe the teacher preceded it with, this is why we're talking about quantum? No.
If they did, I wasn't there for it. Yeah, I don't know.
Single session.
Yeah, it's a single block. Yeah, so you can see all the parts. Yeah.
Kind of a dumb question, but when you have the different transformations,
Mhm.
is there at any point a global phase on any of those qubit states that's like other than one?
Yeah, so as long as you're talking about, these going between these 6 states, then the global phase can be dropped. Obviously, if there's a relative phase, if you have a more complicated state, then it's different. But after we talk about this, we're going to talk about like the math and do all that, so then it'll be more evident. So the idea is you don't leave students at this level of quantum computing in an actual course. You use this to kind of break the ice, let them know like, hey, it's not that scary. If you can play this game, you can do quantum computing. If you can play football, you can do quantum computing. Then we dive more deeply into things like the global phase and all that, and how do you actually determine where on the block sphere a state of a qubit is and so forth. So, yeah. Maybe just go there and here. Yeah.
I have a quick question. New to the quantum computing,
Mhm.
I'm just wondering for the game, when you mention about the rotation of x-axis, it's only the rotation of x-axis, not the entire space, not the typical linear transformation in linear algebra.
So we'll get to the math, and these are linear transformations. So there would be some. So each of these quantum gates corresponds to a matrix, and it's applying to your state, and your state is a vector.
Okay, so it's the entire space rotation or transformation, not only one axis like this.
I'm not sure if I followed, but I see nods, so yes. Yeah.
I just wanted to comment that I know there's been lots of, not necessarily about quantum computing, but there are lots of surveys which they ask students, what's your confidence level about this subject? And there's always huge variations between different countries, or different cultures, different places. And usually the ones I read always like to point out how overconfident the Americans are. And how, in contrast with many other places.
Yeah, I would imagine that you get different results in different places and even different parts of the U.S. So this is in Omaha, Nebraska. We do have a big Air Force base nearby, and Omaha itself is fairly diverse, although rather segregated. So just be honest about the city, right? And those are all things you can look up about the city. Yeah.
Have you tried playing it with like a physical sphere with maybe a little cup holder for the...
No, I have not. I think that exceeds my abilities to build something.
I think this game is great. I'm gonna use it definitely for my class. But I'm just wondering. This kind of illustrates already idea of the superposition, right? Indirectly. I'm just wondering whether you have thought about how to introduce entanglement idea as a part of the game, but then you need another qubit.
So that's what IBM's quantum computing board game does. So theirs is based on 2 qubits. The game is called Entanglion. It's a play on entanglement. So
This is an online game then.
no, it's a board game as well. Yeah. And they also have free assets, so you can print it yourself. You can also buy a professionally made copy. If you just email them, they might send you a bunch. So that's what I did back when they first came out with their game. And I don't know how many they have now, but back then they were like swimming in them. So they sent me a ton. So yeah, Entanglion. And we do also play that game in my class, but once you're ready to talk about more than one qubit. Yeah.
I just wanted to make a comment about the block sphere. You said you didn't build a sphere. We found a way.
I guess I can just use a ball, right? A basketball.
Well, we found a way to do this. We didn't build a ball. You take Tinker Toys and you make axes, and then you have one of those rods, and you
Oh,
can
okay.
rotate. Then you can do multiple operations like
Yeah.
XX or
Yeah.
square root x, square root x.
Uh-huh. and certainly online resources to visualize a cubit on a block sphere, right? There's like a grok the block and all that. So yeah, I wanted to avoid, in general, I try to avoid online things because once you get students on their computers or phones, you can lose them. And so this is my like former high school teacher paranoid self about students with phones. So it's like board game, like interact with a human. Like, yeah.
How have you found this game lands with college students?
They loved
Do
it.
they take themselves too seriously to think, no, they just love it. Okay, good.
Yeah, they love it. Yeah. It works well because they're with their peers, so there's that like level of competition that comes out, or their friends will like smack talk and stuff, and it's like, it's kind of funny because like, once you get the general strategy, which is like move the ball in the right direction, it's really all like luck, but they're like talk as if like they're so good at it, like, oh, I beat you, you know, like, yeah. Same thing with the high school students. Yeah.
So have you thought about framing this game a little more oriented toward experimental physics where you're considering an initialization of the system and then measurements and this intermediate stuff is something introducing the uncertainty. I think this game as it's set up doesn't really I mean, to my mind, I mean, maybe I'm missing something. It doesn't really clarify the experimental side of things.
Yeah, I don't think this game is meant to. This is the start of the quantum unit, and the idea is that you would then spend the rest of the semester digging more deeply into all of the pieces of that. So I'm also a theorist. I work on algorithms, fault-tolerant algorithms, so I assume that there's no noise. I'll talk about quantum error correction, though. Yeah. Yeah.
Have you thought about a level 2 sort of this? Like you were saying, when they get familiar, it's a luck game. A level 2 that doesn't annotate what the arrows do.
I've actually heard that feedback quite a bit. So I was thinking one option would be I could, because if you look at the board, it's the same on both sides. I could have one side not have the labels. So yeah, that's something I've thought about. And I guess the fact that you're also bringing it up just kind of adds to the interest in that. So I mean, I could do that change pretty easily. Yeah.
So the way you have it set up, you're going to go from the game to linear algebra, which is pretty cool.
Well, not exactly. I'll talk about how the course is outlined. Yeah.
You're going to get to that, right?
Mm-hmm.
But it's also helpful from going from linear algebra to the game.
Yeah, so my students don't have linear algebra yet. Or maybe some of the students do, but others don't.
Somebody already does. They're like, what is this useful for?
Yeah, I would say that if your students are better prepared than mine, a lot of the things I do are maybe not necessary, because they're able to think more abstractly, more mathematically. You'll see how I introduce linear algebra, actually, and it's like, yeah, you'll understand. Yeah. Well, actually, this part is new. I didn't introduce linear algebra last year. So, I'm doing time.
I suppose since people are saying that, I'll share that there's a...
We can take a break after this.
Transparency you could put on entangling on that would work well for this, where the circles are vectors and the arrows are matrices.
Okay. I haven't seen like an overlay for that game. I'll have to look into it. All right. So the takeaways for this are students' interest increase from playing the game, but not maybe perhaps due to my poor explanation. But their self-confidence increased for both playing the game and for me explaining it. And overall, they liked the game. They found it easy to learn and fun. So when we come back, we'll dive deeper into like the math and stuff like that. So.